Now that we have completed the list of all our derivative rules, the question now remains, what next? What do we do with all these rules of differentiation, right? Well, what we're going to do is look at how the derivative can be used to solve many other types of problems. I mean, so far we've really just used the derivative to find the slope of a tangent line and the slope of a normal line, but surely there has to be more, and that's what we're going to look at starting now. And what I'd like to do in this relatively brief video is just revisit the idea that the derivative is a rate of change, right? You know, how fast is something changing at a particular instant, and that's why we refer to it as an instantaneous rate of change. So let's say, suppose y equals f of t, right? Suppose that this function represents the amount of some quantity at time t. So some quantity, well, let's say some quantity present at time t. Well, if we were to take the derivative of this function, then what it would be telling us is it would be telling us the instantaneous rate of change of this quantity at some time. So if this is the case, so then if y equals f of t is differentiable, right? We always have to say that because we don't know if the function is differentiable. We've seen functions that are not differentiable, so we have to kind of put that as our little disclaimer. But if y equals f of t is differentiable, at t equals, let's say, t0, right? Then if I took the derivative of this function, this y prime of t, which would be my f prime of t, this would represent, so let's say then this evaluated at t equals t0. In other words, f prime of t0, what does that represent? Well, this represents the instantaneous rate of change right, of this quantity of that quantity at t equals t0, right? And again, it goes back to the idea that we when we defined our slope of the tangent line, we realized because of how it is sort of related to the average rate of change, that's why we now describe this derivative as an instantaneous rate of change, right? And what you'll see in a lot of these problems is that you'll see t being used because it often represents time. All right. So let's just do a few examples of this concept. So I'll give like a variety of different types of functions, and then we will see what the instantaneous rate of change looks like. Right. So the first one. And I'll use some familiar functions and then some not so familiar functions. But for instance, you might remember this formula from an application of exponential functions, right? Where you have P is a principal amount of investment, so money, right? So principal amount. And then your R is typically your annual interest rate compounded continuously. So this is your annual interest rate compounded continuously, and that's what tells us to use this. And sometimes it's referred to as the PERT model. Um, but if it's compounded continuously, that means at every instant your money's earning interest for you. Now, isn't that a novel thought, right? Compounded continuously. And then T represents the term of investment, again, typically in years. So T is the term of investment, usually in years, right? So since your interest rate is an annual interest rate, you usually have your term of investment in years, right? So let's say, for instance, we invested $1,000, and let's say we're going to have a fixed, let's say it's a fixed annual interest rate of, I don't know, let's say our R is 3%, again compounded continuously, and then we're just going to let this thing grow. So we're going to make a one-time investment, and we're just going to let our money grow based on this model. So then the amount function, and that's what A represents, A for amount. Maybe I should put that over here. Right, so the amount in whatever this account is, well, the formula is it will be my initial investment of $1,000, and then it's E times, and typically we represent our percent as a decimal, so 0.03, and then that will be my exponent of 0.03 T, right? And then this would be, again, in dollars, right? So this is our function now that gives us the amount that's present at any given time. So for instance, if I wanted to know what is my amount 5 years from now, then I would plug T equals 5 in. So I would get this. And then it would be e to the 0.03 times 5. So that's 1,000 times e to the 0.15. And then this, being an irrational number, let's go ahead and approximate it. And since this is a dollar amount, let's round it to 2 decimal places. So the amount present after 5 years, again, assuming we make no withdrawals and no additional deposits, it's going to be $1,161.83, right? That's not great. When you think about it, we started with a $1,000 investment, so we've really just earned a little over $160 over the course of 5 years. So, not great, but I'll take it. And that amounts to a pretty low interest rate, right? And again, a lot of savings accounts out there, you're lucky if you're getting 3% return on your money. But that's the amount, right? So that's all algebra. So now let's see, for instance, what is the rate at which our money is growing at this time. So at this instant, how fast is the amount growing or changing in our account? For that, we would have to use the derivative, right? So let's take the derivative of this function. And this is certainly not the most complicated derivative we've found, right? So we use our constant multiple rule, bring down the 1,000, and then we have to apply our chain rule for the e. So it's going to be, we'll get back the e to the 0.03t, and then I have to multiply by the derivative of what's inside. And the derivative of 0.03t with respect to t is 0.03. Now, as far as simplifying this, again, we can use our commutativity property and multiply the 1,000 and the 0.03, which is going to give us 30. Let's see, 30e to the 0.03t, right? So this now gives us the rate of change of our amount at any instant. So again, let's say we wanted to know how fast is our money growing, after or at t equals 5. So a prime of 5, well, now plug 5 into the derivative. So we will have our 30 e to the 0.03 times 5, and that's the same 30 e to the 0.15. Notice the only thing that's different is the coefficient in front of the e, and that's not surprising because we know how the exponential function operates as far as derivatives are concerned, right? And if we do the 30 times the e to the 0.15, we will get $34.86. Now, it's dollars, but it's a rate, so it's dollars per year, right? Now, the way we can see what the units are, if we write this derivative, or in fact, let me go one step back. If we write this derivative using the Leibniz notation, meaning in terms of d's, so this is dA dt, then you simply look at the units of this variable. So the units of the amount, that would be dollars. So this is in dollars. And this variable, time, well, that's in years. So this is my variable in years. So it's the rate of change of dollars with respect to time, which is measured in years, right? So that's how we get the $34.86 per year. So again, let's actually write a single sentence that would be like a good sort of interpretation of these two numbers. It's one thing to carry out formulas and processes and just plug stuff in, but what does it really mean? So let's write a sentence that summarizes these two numbers. So at time t equals 5 years, right? The amount present, right, in this account is the $1,161.83, and it is changing. That amount is changing at a rate of $34.86 per year. So, and the amount is changing. In fact, we could actually say is increasing because this is a positive rate, meaning that the quantity is going up. But I'll just say is changing at a rate of the $34.86 per year, right? If we were to repeat this process at, let's say, year 8, then we would have a different amount and a different rate of change, right? And that's the whole idea of being able to compute rates of change at different instants, all right? So there's one example. Let's do a second example, and this one is not really it's not something like a known formula, but I'll just say this. So let's say at time t, the amount, let's see, so the amount of water in a tank is given by, so let's use, I'm going to choose a random variable here. Let's say q, right? So like q of t, and here's our function. 200 times the quantity 30 minus t squared, and then this is in gallons, right? Right? So at a given time, we can use this to tell us how much water is in a particular tank at a certain time, right? So the water might be flowing in, might be flowing out, we don't really know. But certainly, the fact that this is not a constant, it means that the amount is changing with respect to time, right? So as time goes on, either more water flows in or more water flows out, or it could be a combination, right? You could be pouring water in and the tank is leaking, all that stuff. So it could be any particular scenario. But what we have is we have this amount function here, right? And let's ask this question. Oh, and let's say, so Q is in measured in gallons and T in minutes, right? So, and T is measured in minutes, right? A unit of time. So here's our question. How fast is the amount changing? Right, so the amount of water changing at t equals, let's say, 10 minutes. Right, so maybe maybe there's a situation where you turn on a hose and you're filling up this tank, or you open a faucet and you're emptying the tank, and after 10 minutes you want to know how fast is the water, either the water level rising or falling, right? And the key here is how fast, right? So this phrase, how fast, is interpreted as what is the rate of change, right? How fast is the amount of water changing at a particular instant, right? So that indicates to us that we have to find an instantaneous rate of change. So for that, we have to take our derivative, right? So if I wanted to use the d notation, it's going to be dq dt. Now, for this type of function, we have a choice, right? We could either expand this binomial and just use a couple of our basic rules, or we could keep it in this sort of factored perfect square form and use our chain rule, right? So again, it's always good to get practice with the chain rule, so let's go ahead and use the chain rule. So we're going to bring down the 2. So this is going to be 400, and then we keep the inner function, subtract 1 from the inner function, from the power, sorry, so we'll have 2 minus 1, and then times the derivative of the inner. But the derivative of the inner is just negative 1, because the constant goes away, and then we have a negative 1 times t, and the derivative of negative 1 times t with respect to t is negative 1. So here's our derivative of our amount function. So we have a negative there. I can put the negative in front of this whole product. So it's negative 400 times the quantity 300 or 30 minus t, and then now my power is 1. So if I wanted to, I could actually distribute the negative 400, and I will have a negative 1200 and then plus 400t. Or let me write it like this: 400t minus 1200, right? Actually 12,000. That's 12,000, not 1200. There we go. And now, again, the units for this would be gallons, right, per minute, right? And now, since we're given this specific time, all we can do, or all we need to do, is just evaluate this derivative at that particular time. So how fast is the water level changing at this point? Well, take your derivative and evaluate it at t equals 10. So if I plug t equals 10 into my derivative, I'm going to have 400 times 10 minus 12,000, right? Well, that's going to give me 4,000 minus 12,000, so that is negative 8,000, and then this would be gallons per minute. Wow, that's a huge rate of change, right? All right, but yeah, so what does this negative mean? It means that at this instant, the water is decreasing at a rate of 8,000 gallons per minute. That is fast, right? So again, let's write a little sentence that interprets this number in the context of the question, right? So it's not just that it's in some arbitrary instantaneous rate of change. We know what the function represents, so we can interpret it in context. So what this means is at t equals 10, right? That's our instant. So at t equals 10 minutes, the water, or water level over the amount of water, is decreasing because of that negative rate, right? Is decreasing at a rate of 8,000 gallons per minute. So we wouldn't say that it's decreasing at a negative rate. No, it's decreasing at this rate. So the negative sign is interpreted as a decrease, and then it's decreasing at this rate. And again, if we had a different value of t, we could come up with a different rate of change, right? So, I mean, nothing in terms of, new rules, because we're done with the rules, right? We've covered those, and we're getting better and better at them every day. And now we're focusing on ways that we can use the derivative to solve other types of problems. So I thought this would be a good way to kind of remind ourselves that at the very basic level, a derivative, yes, it represents the slope of a tangent line, but it also represents the instantaneous rate of change of a function. All right. If you want to see more applications and uses of a derivative, why don't you tune into the next video? See you then.